so back for part 4. We left off looking at this indeterminate form for our limit, and we started talking about how we could factor that x cubed minus 1 into this difference of 2 cubes. And so here's what this will factor into. We see that we've got a factor of x minus 1 and x minus 1 in the numerator and denominator here. So we can go ahead and factor those out and divide. And so really we can look at the limit of a simpler form of our rational function, which in this case would be x squared plus x plus 1. Well, now I've got a polynomial function. I can go ahead and do that direct substitution. I don't have to worry about the denominator equaling 0 anymore because we've divided it out. So when we do that, we find out that our limit is 3. Okay? The big thing to understand, as we've talked about in previous math classes, is that when we look at this simpler function, we still have to realize that x cannot equal 1. We put that stipulation in so that we realize that, hey, that will give us an equivalent form of our original function, that x cubed minus 1 over x minus 1. Okay? So it kind of leads to what you see here. So let's see the real number and let f of x equal g of x for all x's that don't equal c in an open interval containing c. If the limit of g of x exists, then the limit of f of x exists, and we can see that as x approaches c, those two limits should be equal. So basically what we're saying is this. If we can get something down, take a function and get down to a simpler form, an equivalent form that's a little bit simpler and easier to go ahead and determine the limit of, then it's okay to do that. So that's what all of this math stuff here is telling you. So one last example involving that, at least in this type of situation. So the limit as x approaches to of this rational function, again, if we do a direct substitution, we're going to get 0 over 0, which gives us that sign that, hey, something's up here, we should be able to kind of change this a little bit to an equivalent format that's a little bit easier to work with. So trinomial, we notice that, hey, factors of negative 6 that add up to positive 1, we can factor this out into x plus 3, x minus 2, divided by x minus 2. And so we see that those will cancel out. I can look at the limit now as x approaches 2 of just x plus 3. And so that I can easily find the limit of, and I know that my limit is 5. Okay? So factoring can help us get away from that indeterminate form that we have and actually figure out the limit algebraically. All right? So hopefully that makes sense. In terms of trig functions for the most part you can go ahead and do direct substitutions into. Obviously things like secant, cosecant, tangent, and cotangent we've got to be mindful of because those will end up as fractions or as rational functions when you sit there and kind of change them into their other forms. But we should be able to evaluate those trig functions at whatever value of x we're approaching, usually known as c. Okay? There is something else that happens sometimes where we get that kind of indeterminate form. So we've talked about in the past, in other math classes, about rationalizing the denominator. But we have a rationalizing technique that can help us with the indeterminate form of the limit as well. So take this example as the first case for that. The limit as x approaches 0 of this function. If we do a direct substitution, we get the square root of 1 minus 1 over 0, which obviously gives us that 0 over 0, or that indeterminate form. The problem here is there's no factoring involved. How am I going to factor the square root of x plus 1 minus 1? If I really wanted to, I probably could. It involves some fractional exponents, but what am I going to divide it out with? I don't know. So what happens is we turn to this process called rationalizing the numerator. And so just very much like rationalizing the denominator, we're going to do the exact same thing. So here I need a conjugate, which would be the square root of x plus 1 plus 1. I need that in the denominator as well. Because whatever we do at the top, we have to do the bottom. Okay? And so we'll multiply this all out, and I'll show you what's going to happen next in part